Okay, recording now. So, okay, so I propose a new, so I was explaining what's like a review of what we did in the previous video. So I was talking that if I have a reaction or a random process that has a transition between two states with a given rate, I can produce a new time to reaction using the Gillespie formula that is -1 over lambda logarithm of R. R is a random number with a uniform distribution between 0 and 1. And once I produce my new time to reaction, it can be, and it has some value. And I also define a time for next data acquisition. Usually this is a delta t. So this guy has a value of delta t, usually is constant. Okay, so if the reaction occurs before, what I do is I perform the reaction, and the new time for acquisition is not delta t, but delta t minus this tr. So it's going to be this. So now I move forward on time at time tau tr, that is going to be the minimum. And now my new time for data acquisition is going to be less because I move forward on time. And the new time for data acquisition is going to be this, and this guy is simply delta t times dr. So this can happen multiple times. If I have, for instance, I produce a new time and the new time is just this, I do it again, and my new time for acquisition is going to be now this new time, and I do it sequentially until, and I perform the reactions every time until my new time for reaction is bigger than the time for data acquisition. So what do I do that in that case? Given that my data acquisition is before the time to reaction, I do the opposite. So I go and move forward this time. There's going to be this. I export data, and given I just export data, my system shouldn't change. My system doesn't change during this time because there's no reactions during this time, only data acquisition. And now my new time for reaction is going to be this one. And this guy is my previous time to reaction minus this guy. That is like the previous time to export minus this guy. So this guy, if I call this guy time for exporting, is not delta t anymore, but it's simply time to export. And I do this sequentially, sequentially, sorry. So depending on which is the minimum, I subtract the other, and I propose a new time. So after doing this, I export data, and my new time for data acquisition is going to be again delta t. So a new time for acquisition is going to be delta t, and I move forward on time. Does it make sense? And I am now in this condition now. So and I close the loop of the reaction of the algorithm, sorry. Okay, so yeah, last time I was explaining you the Poisson process. So the idea is essentially the same. So first I propose a time for reaction following the Gillespie formula, and a time for exporting data. That is going to be delta t. My initial state is 0, or the initial amount of protein is 0, and the time for reaction, or the total time, is t. I define my delta t as a fraction. It can be as small or as big as you want. This can be, if you are, for instance, interested only in exporting data at the end of the experiment, or this can be as big as you want. It doesn't have to be small. Yeah, but I prefer this like delta t because it's kind of a good resolution for the image you're gonna get. And I calculate the minimum between them, and the reaction is gonna be the argument of the minimum. So the minimum is this, the result of this function is gonna be 0 because it's the first element of the array, and it's gonna be 1 if the minimum is the second element of the array, that is element 1. So one way, for instance, is of the experiment is try to estimate the time for reaching a given number or a given state, in this case 15. So I do sequentially the same, calculate the minimum between them, and the reaction is the argument of that minimum, and I move forward on time this minimum. Okay, so if the minimum is time for exporting data, I subtract the minimum to tau r. If I have multiple reactions with multiple timers, I subtract this minimum to all of them. I export data, so exporting data is just append or like concatenate these arrays. So in the array, you're going to have the number of the cell, because I'm doing this for multiple cells, the time, and the state, in this case, the number of molecules. And new time for, I propose a new time for exporting that is going to be delta t. It's like a reaction that occurs with deterministic time. Otherwise, if the reaction is like increasing the number of molecules, I subtract, now in this case, given this reaction, I subtract the tau for the other times that are not the reaction, in this case, the time for exporting. I increment the number of cells, of number of molecules, and I propose a new time for reaction because this is the reaction, or like the molecule increment. And in the end, I save the data when it reaches the value of 50. And I do this for 1,000 cells. So I have to run this again. So this should be in the script that you have already, that I sent to last time. Where is it? Sorry, I'm lost. Here, I think, yeah. And I save, once I have this array data, I make it a data frame, and the columns are cell, time, and state, in this case, number of molecules. And I'm gonna get something like this if I plot all the cells. And this is the typical Poisson process. In this case, I stop when it reaches 50, and I do a new cell. You can also stop if you reach a given time. But this kind of simulations helps you to get the first passage time of reaching a molecule. That is also some relevant problems. So for people that are in the theoretical like part of this class that is given by Professor Singh, this distribution follows an Erlang distribution. So I can compare this with the Erlang. We can do this again. Plotting. So here I'm plotting the first 100 trajectories, and they look like this. And you have like the convolution of 50 exponential distributions. So it's going to be a Erlang with mean 50 and sigma square 1 over 50. So here I use the stats for importing delta, and I plot the PDF of Erlang distribution with a mean 50, and you can check, but this has like the properties you need for like to obtain from the theory. And I compare this with the histogram of the first pass at times. So I get something like this. Okay. So here is like that we do for the Poisson experiments using Q in theory or Poisson distribution. So we can modify a little bit this script for making some other like complex models. So I was thinking, for instance, how to change this to make a perfect process. So what's the idea? So the perfect process is the simplest mechanism or the simplest model for modeling gene expression or the production of cells in production of molecules or proteins inside a cell. So essentially you have different states that represents each of them different molecules. So you have 0 molecules, you have 1 molecule, you have 2 molecules, etc. So the production is going to occur with rate lambda, similar to the Poisson process. That the Poisson, remember, is the previous one that I told you. That is just accumulation. But each of the cells have a lifespan of gamma. Just remember that it's like this queuing theory with infinite number of servers, and each of them serves each person with a given lifespan. So essentially, you have like the degradation or the rate of decreasing is going to be proportional to the number of molecules. So here you have 1 molecule. So the transition rate from n to 0 is going to be a constant times 1. It's going to be simply lambda. And the transition between 2 and 1 is proportional to 2 because you are coming from 2. And the same for 3 times lambda, and so on. This guy comes from 4 lambda, and this goes to infinite. This gamma, sorry. And so on. So what happens? So if I have a given number, I have essentially two possible reactions, or producing 1 molecule or decreasing the molecule. So we have 2 reactions. So you have the first reaction is going to be production of cells. So I can simulate the time using the Gillespie. And the second time is the same. So now the rate is lambda, or overall n times lambda. And I do the same. I take the minimum, and depending on which is the minimum, I perform the reaction of the minimum, and I calculate again I subtract the reaction, or depending if the state changes, I have to calculate this again. So let's do it quickly. Okay, so I'm going to use the same script of Poisson process. So I'm gonna copy and paste it. Sorry, paste it here under the Erlang. So I have here the script for Poisson. So here I only have one reaction, that is the production. So we're going to add another reaction that's going to be degradation. So here I have, let's say, degradation gamma equal to 1. This is the rate of degradation rate. And let's say start with 10 molecules. We're going to call S the same as the number of molecules. We can start from any number, but let's start with 10. And the second reaction is going to be something very similar. So you're going to use the type of degradation, time of degradation. And as I was telling you, this is going to be proportional to gamma times the number of molecules. And in this case, I carried S. So if you feel lost, I change name as, I can use N. Let's use N for not getting confused. And now we have 3 reactions. So that I have the first reaction that is the data acquisition, the time for production, and the time of degradation. Okay, so I add it in the next element. And the same, I calculate the minimum and I move forward the time the minimum. Okay, the first reaction is sporting, so I do the same, but now the number of molecules is N, and I subtract the tau for the other reactions that are not exporting. So I have 2 reactions here. So we have degradation and production. Okay, so the second reaction is molecule production. So I do the same, and I subtract the minimum from the other reactions that are not production. So I have the second one that is degradation, and I subtract the minimum. And I perform the reaction. The reaction consists on producing 1 molecule. So N goes to N plus 1. And I calculate a new time for reaction. So what happened here, the thing is like the time of the rate of degradation depends on N, and N has changed. So the propensity, this propensity has changed. I'm not here anymore, for instance, but I'm here. So my new propensity is now changed. So given that my new propensity changed, I have to calculate everything again. Okay, so if my propensity was the same, this was correct, but now that my number changed, I have to calculate again a new time for degradation because my number changed. Otherwise, I can keep this. Okay, so I'm going to comment this, but in the general case, it should work. So this is if a reaction is 1. And if reaction is 2, I'll do something similar, but with the degradation. Okay, so time to experiment. And remember, in this case, given like the propensity is always lambda, doesn't matter of N, I don't have to recalculate the lambda. However, given the properties of the exponential distribution, it's going to be the same. It doesn't matter if I calculate again or not. Yeah, but for keep the consistency, I'm going to subtract my tau from the time to reaction. This is going to help us with some more complicated simulations. If this time is not exponential, I have to do this. If the time is other kind of process, this should work in most of the cases. And if my number of proteins is, well, my reaction is degradation, so I make the protein or the molecules decrease it by 1. And I calculate the new time for reaction, so I know this, and the new time for degradation should be calculated because n is changing. Okay, so I think is 5 is okay. So this has to be equal, and this has to be 2. Can use else if okay, so that's what happened here, division by 0. Okay, so the problem here is like exactly. I found a problem here is like this guy, 1 over n is not defined when n is 0. Why? Because once I'm here in 0, there's no degradation. Okay. So it means it can be interpreted in different ways. One way is like the time for degradation can be infinite, or that we can ignore that reaction. So it depends on your choice. So what I do usually is like if n is equal to 0, I say that this guy is infinite. Because it's very big, it will never happen. So in simulation, when you want to say that something is infinite, you just say that that you add a sign or you give it a very big number. Else, use this guy. So we can use this condition when the number is 0. Remember Python, use the indentation. So for using the if, inside the if is everything that has this indentation. I'm using here the tab key. And I do the same here. Let's see. Okay, this should work. Just to, okay. And I'm going to have the same plot, or save the data and plot. Here when I'm exporting, I'm exporting here. I can plot. And usually what would you do for checking this is to check the mean and the variance. So you can, I mean, I don't want like to teach you much theory, but there are like ideas that is well known. So if for any Poisson process or Berthet process, essentially like the mean of number is simply, in this case, is going to be the production rate over the degradation rate, and the variance, because it's a Poisson related process, is going to be equal to the mean. It's going to be equal to lambda over gamma. So we can like compare this in a steady state. So I save here the data, and I can plot the 100 cells you have here. Sorry, I shouldn't plot this guy. So here you have 100 trajectories of Berthet process. Okay, I can make it smaller to show you better simple trajectories. So the thing here is like the minimum. Sorry, the mean is going to be simply 10 because lambda is 10 and gamma is 1. So the mean is going to be lambda over gamma, that is 10. So I can plot this. Plotting 10 times 10 is an array of like a Python array. If I multiply a Python array by a number, like integer number, is going to give you an array of a number. Yeah? For instance, here I have an array of 3 times 4. You're going to get an array of 4 elements, each of them being 3. It's like a trick using Python. So now we have an array of 10 with the length of tr. So tr can go from 0 to 10 in this case, and you have something like this. Yeah, so essentially, like the mean of the process should be. I can also like compare the mean and the variance over time. So I can estimate here the variance using this script that was before, and so here the name is tf cells. And I can save. I can plot also the. Sorry here. So you're just gonna cut and paste this and plot the mean that I'm calculating here using this script that takes cells at a given time and calculate the mean. So I can plot here ef dot time and df dot. Sorry. df dot time and df dot mean state. So one way for checking that your code is correct is always compare the results with a theoretical result that you know. This you can use here, I don't know, blue. Like to compare them, they match kind of perfectly, and I can also plot the variance. So if you compare the results of your moments of your simulation with something that you already know, it's like the best way to check that your simulation is correct. So this is the variance over time. Yeah, so as you see, like at a steady state, like when you reach stationarity, the variance goes to 10. That is the thing I want to, approximately is the result, the theoretical result. Okay, so after that, another application from this algorithm is just simply the proliferation of cells. That are other kind of theory that we have at the lab. So what's the idea? You start from one individual and you reproduce your population at a rate proportional to the population. Okay. So you have a given division rate, and the transition between states is proportional to the number. So this guy is going to be 2 times n, and this guy is proportionally 3 times lambda. Sorry, the transition for 4 and so on. So essentially, like the transition for n to m plus 1 is n times lambda. So I think you studied this in the theoretical part of the course. So the result is as a function of time, the result of the distribution is a geometric distribution with a mean essentially the solution is n is going to be a geometric distribution with a mean e to the lambda t. Okay. So it's just taking the same script for Poisson distribution for Poisson process, sorry, and you change one line. So I already have it here. It's already in the script I sent you Wednesday. Now the transition time is just lambda times the state, and that's it. I have to start from one because if there's no individuals. What's the problem? Okay, so their solution is going to be something like this. And I'm going to plot different trajectories. And also I compare the mean and the variance. In this case, the mean, we compare the mean with the exponential distribution. As I told you, this is like the matching. And the CV square, that is the variance over the mean square with the known solution using the geometric distribution, is 1 minus exponential to the minus lambda t. So here you see the CV square. So I don't want like to stop very much on this, like only let you guys know that this kind of simulation exists, and you can like verify more with the scripts I sent to you last time. Okay, so today my plan was like to show you how change this, but overall everything is like the population over time. I can use the log scale here, like make this y-axis log. You're going to get something like this. Okay, but the idea is like now what happens if I want to simulate continuous process, not with this discrete statistics. So let me explain you better. So far, this kind of simulation using the Gillespie formula gives you the time of transition between two states that are essentially discrete, or you can count 1, 2, 3, or you can model using discrete numbers. However, in some cases, your variables are not discrete and rather continuous. So I can start from a simple example that is, you can also like model the gene expression, but the thing is like you cannot, in some cases, you cannot measure explicitly the number of molecules inside the cell. What you measure is something related to the number of cells, or say concentration. That can be GFP, can be like fluorescent markers. So what you've measured actually is the concentration. concentration. So this Berthet process has this limitation that it cannot model the concentration. And the concentration essentially increases because production of the molecules, but decreases continuously given the growth of the cell growth. So one simplification that we do at the lab is using the known model of burst dilution. So what's the idea of the process? So essentially, like we use this kind of diagrams for representing this kind of hybrid systems because you have discrete jumps that you can quantify. You have one burst, two bursts, three bursts, but you have also continuous dynamics. So essentially, you have production of a given number of proteins, and then it decreases given degradation. That suddenly it increases and decreases by degradation and so on. Okay, so we usually model our system using differential equations. Let's say the one we use for protein concentration is the x, the derivative of the x is going to be the concentration. X is equal to minus a given degradation rate, the dilution rate, sorry, gamma times x. And I'm going to perform some jumps here at a given rate. So usually there are measurements that show that this burst dynamics occurs with exponential duration time. So you can consider this as a Poisson process with a given rate lambda. So you know that if there's a Poisson process, the time between this bursts tau r has a exponential distribution that you can quantify or you can estimate using the Gillespie formula. And every time this burst occurs, your protein is going to increase by a number b. So there's different ways like to model this. You can start, for instance, saying that b is 1. You can say that b is a given number, or you can say that b is a random number. Experimentally, they also found, I think Avi also explained in the theoretical part of the course that the burst size, that is the number of proteins produced during the time lifespan of RNA, is also exponential. Sorry, it's geometric. It's geometric, but the equivalent continuous of the geometric distribution is exponential. No? So we can do the same exactly, like proposing the time for next reaction. Next reaction is going to be next jump. Next jump is going to occur at time exponentially distributed. But the thing is, like during this time of multiple reactions, the concentration will change. Specifically, it will decrease following the exponential decreasing. So today I sent you this script. You can verify later with the video. So this one is the previous one. So the name is continuous simulation. So here you have like the idea. So I can like make it again, explaining step by step. So essentially what I did was like to take the script for Poisson process and modify it to make a discontinuous case. So the same. So my parameters are lambda, that is the rate of burst of burst occurrence, and gamma is the degradation rate. I propose delta t, that is the time for data acquisition, time. This is my state. I'm going to start from x equal to 0, and this is the time for finishing my simulation. So the next time for exporting is going to be delta t the same, and the next time for reaction Gillespie, and I calculate the minimum of both of them. So calculate the minimum, but now the trick is that during this tau, my equation or my continuous state will decrease, because like the solution for this differential equation simply is going to be x is equal to x at time 0 times e to the minus gamma t, and this cell is evolving, or like my state is evolving during this tau. Okay, so I have like my continuous system is decreasing continuously, and the rest is essentially the same. If the reaction is export, I subtract the time for the next burst to the time to sorry, I subtract tau to the time to the next burst, and I'll save the data, and the new time for exporting is gonna be dt. And if it's the opposite, I do the opposite. I subtract tau for time to exporting, and I perform the reaction. This can be essentially x is going to be x plus something. So you can use whatever you want. If you want, let's say, to increase only one molecule, it's okay. And you propose a new time for reaction. And I do this for 1,000 cells. It's gonna take some more time. So let's start this out with for 100. As a control is the same. Sounds right. Yeah. So I save it and I plot temp trajectories. You're gonna get something like this. So you can see here the production and the degradation of the system. And again, like the steady state is going to be lambda over gamma. So lambda here was 10 and gamma was logarithm of 2, but I can make this 1 if you want. And my state is going to be 10. But in this case, because gamma is different than 10, I'm going to get another steady state. So you can check like how to get this equation, but it's not part of this. I don't want like to complicate how to get obtain this, but this is like the idea. And the steady state is going to be 10. Okay, so I can make this a random exponential as well. And anytime that the mean of the bursts is also 1, I'm going to get the same steady state distribution. Usually, the mean of this system is going to be the production rate times the bars over the gamma of this guy, the mean of the bars. So these bars can be another random number, but anytime that I mean, you only need here the mean of that number. So the mean of an exponential variable is exponential, is 1, sorry. Because here beta is 1, something like that. Okay. So I have something like this with random bursts. I can estimate here the mean and also the variance. Here the variance change a little bit. Yeah, but because I modify here the script, but anyway. So let's skip this, and that's the idea. So another system that we can model is the cell size dynamics. So what's the idea? So you have cells growing exponentially over time, and then they divide over 2. So partition, so you have cells, let's say bacteria or whatever, that are growing exponentially. And at a given time, they divide by 2. And they are keep growing and so on. So I'm going to neglect this one and only track one of them. So you're gonna get trajectories like this over time. This is the cell size. And this is the time. So the cell is going exponentially, and then division, exponential, and then division. Okay, so how can we model this system? So here, if I say that my cell size is S or X or whatever, let's say X because we're going to see X. If the cell size is growing exponentially, I have that the growth rate, let's say, is, what did I use here? Gamma S, and this jump occurs at a given rate, such as S goes to S over 2. Okay, so there are different. Sorry. Sorry. Yes, thank you. So here is X. So there are kind of different models. So I'm going to use as explanation. I'm going to use a transition rate proportional to the cell size. So the rate is going to be K times S. K times X. Okay, or yeah. So how can I calculate the, so the thing here is like X, or this transition rate is proportional to the state, and the state is evolving continuously. So this time, or this transition times are not exponential anymore. So for estimating this, I can use the Passer equation as well, as I did in the previous session. So essentially, I'm doing a single step process that jumps from no division to division. And this is occurring at the rate K times X. And X, the thing is, X is the solution of this guy. So X is going to be X at time 0 e to the gamma t. So here X depends on time. So here it comes like the tricky part. So be vigilant. Okay. So if x is growing as this, and my master equation is dp0 over dt is equal to the flux x to the x0 times 2x0 e to the gamma t times p0. So it's negative because there's an efflux, and dp1 is dt is equal to k x0 e to the lambda t, sorry, gamma t p0, that is equivalent to k x0 e to the gamma t 1 minus p0 because p1, sorry, because p0 plus p1 is 1. So I can solve this equation. Make sense? And when can I delete, erase? Let's see, clear this guy. I have simply dp1 over 1 minus p1 is equal to kx0 e to the lambda t times dt. So the solution of this guy is going to be logarithm minus logarithm of 1 minus p1. And the solution of this guy, I mean, I'm integrating now. The solution of this guy is x dot k times e to the lambda t minus 1. That's the when time is 0. And the solution of this is p1 is going to be 1 minus e to the minus k x0 e to the lambda t minus 1. Okay. So remember the idea of the Gillespie formula. This is a case where the Gillespie formula is not constant, but still it has solution, analytical solution. So the idea is I toss a random number r from 0 to 1. I plot here the cumulative p1 over time. Can follow any way, I don't know, like something like this as well, whatever, but it's this p1. And I pick a random number here, and the projection of that random number to the p1 is going to be my time of reaction. So in the case of exponential distribution, this guy was only one, just 1 minus exponential to the minus t. So the solution is the one we know. In this case, I have to solve for t to get the solution. So I have to use this is equal to a random number r, and I solve for t. Okay, so the solution is going to be time of reaction is 1 over, this is gamma, sorry, 1 over gamma logarithm of 1 minus gamma over k x0 here and logarithm of 1 minus r. Okay, so this is kind of different, or like something different from what we find in the GLSP formula, but anyways, it's also analytic, so we just can use it. Okay, so I have something like this. So here now my random number is going to follow something like this. I can use, in this case, I used k equal to lambda, such as this guy is 1. And this is the cell size in the beginning of the cell cycle. Okay. So it turns out that the size is S. So I start from size equal to 1. This is my next time to division. And I do something similar. Post reaction time, exporting time and reaction time. Select the minimum. During the reaction, I let the system, the continuous system, to evolve. In this case, it's growing exponentially. And after this tau time increases, I export if the reaction is exporting, or just division if the reaction is division, and I calculate a new time for reaction that is going to follow this same formula. Okay, so I have something like this. So let's do this with 100 for making faster. And I'm gonna get something like this. Okay, so cell size are growing and then divide over half. And you have trajectories like this. This is the mean. The black is the mean. And you can also estimate the variance and so on. So this is the particular case when the transition times is a Markovian process, or the division is a Markovian process, because you can define a rate. In this case, the rate is proportional to the cell size. No? So it's kx times, k times the cell size. But in the general case, the division is not, you cannot assign or give a rate, but you can only say that it follows phenomenological process, a phenomenological model. So I don't know what to do. I can continue this quick. So essentially, like, it's known that the size of division is going to be the size at the beginning of the cell cycle. Let's use X again. So, okay. So cells are growing and dividing. Okay, so let's call this guy after the first division size of bird, and this guy at the end size of division. And this difference is going to be size delta, that is usually the size at division minus the size at birth. Essentially, like, a simple model is saying that this delta is an independent random variable. And you can give it exponential distribution or whatever. So delta can have a given distribution. I usually use gamma. Gamma distribution with a given mean and a given CV. CV, remember, is variance over the mean. Okay, so I don't want to, it's variance over the mean square. I don't want to go in details of this, but essentially, like, given this, the size of division is also size at birth e to the growth rate, gamma time to division. And I can also use this, like size at division is just size at birth plus delta, and this delta is a random variable. So I can use these two guys and equate them, and I'm gonna obtain that the time for division is going to be 1 over gamma logarithm of size at division is size at birth plus delta over size at birth. And I can use this formula to obtain, sorry, this is here, time to division. And I can use this formula to obtain any division time. So I did that. And so I propose a added size, and this delta is our gamma distribution. The time for reaction is now 1 over gamma logarithm of S size at birth plus added size over size at birth, but here you can cancel this guy out and you have only one. And so on. That's the idea. So now you're gonna get something like this. A cell size is something more what you find in experiments. You find these oscillations in the mean cell size. Okay, maybe you're interested, you can go and focus a little bit more on this. I know that people are working in other projects, but I wanted to show this. Okay, so what else we have? Finally, so we were discussing with you guys about modeling the neurons. So let's spend the last time for explaining that system. So what's the idea? So you have some neurons. I don't have prepared yet, like here the data, but these neurons, essentially, there's a wave of voltage traveling through the axon of the neuron that corresponds to a given train of pulses. Okay, so there's a pulse produced by, in the neuron that travels to the end of the dendrite. That is like what we call a synaptic pulse that has some frequency of arrival. So usually when you have arrivals, you model it, the time between arrivals as a Poisson process. So what happens here, and you have here another molecule that we're going to call it postsynaptic, because synapsis is the process of transmitting like this information from one neuron to the other. So inside here, you have like the union between two neurons. So you have essentially a given number of vesicles filled with neurotransmitters that are molecules that has some molecules inside. And when they can like increase or decrease over time. And every time a new pulse comes to these vesicles, you can release some of them different right through the membrane, and the neurotransmitters are liberated such as they can excite the next the postsynaptic neuron membrane, and depending on how many neurotransmitters are like in the new membrane, in the new cell, you're gonna have a new electric pulse. Okay, so the idea is more or less, without this level of detail of biology, is I'm going to model the voltage of the postsynaptic cell. Okay, this voltage is going to be UV. So I'm going to say that UV is decaying at a rate gamma times V. So this is the derivative. And the number of vesicles here is N. So I'm going to consider concentration of vesicles or make this vesicle number a continuous variable.
Cesar, but that should be a negative coefficient in front of the
I think. Yeah, why? Because the voltage is decreasing over time because there's some charge that can be getting out from the, if I'm right, no? From the cell. So the number of vesicles in the presynaptic cell, we're going to assume that it's going to increase until reaching a given maximum. So it's going to be K times this maximum minus N. Okay, so essentially when this N is equal to M, there's no more production of vesicles. And every time, so the pulse is arriving, or the presynaptic neuron is arriving at a frequency, let's use lambda here, but you use F, but like to keep consistent with the Poisson process, I'm going to use lambda. So it's going to arrive a pulse, and every time the pulse arrives, a certain amount, every vesicle is going to be released with some probability. So if you have, let's say, n cells, essentially n times the probability is going to be released. So n goes to n minus n times the probability. Like being very, it's the first order. No, you can also consider the number of vesicles to be discrete, and the probabilities Bernoulli process, etc. But here I'm going to use this simplification, and the voltage of the postsynaptic cell is going to increase for a constant times the number of released vesicles. It's going to be, sorry, here. V goes to V plus this guy. And if the voltage reaches some threshold, you're going to send a new pulse, and the voltage goes to 0. So I modified I modified this model to consider the neurons. So I put here all my variables. So the idea is like this can be lambda, but I use F. Okay, so this is my frequency of incoming pulses. This is the production rate. This is the maximum number of vesicles. This is my initial voltage, and this is my threshold voltage. And this is the probability of releasing, and this is the constant that is by which the voltage is increasing. Okay, so the same. I have one reaction here that is like the incoming voltage. It occurs with this. It's a random Poisson process. I select the minimum of exporting under reaction, etc. I increase the time by tau and the number of molecules, because it's this equation, this differential equation. The solution is an exponential function of time, decreasing exponentially, so it has here the negative. And this is the solution for the number of vesicles over time. And I perform the reaction. If it's exporting, I export. If the reaction is reaction, my burst is going to be n times the probability, and my voltage is going to increase proportion to the number of released vesicles. And if the voltage is bigger or equal that a given threshold, the voltage is going to reset to 0. Okay, so the result is something like this. Okay, so you increase and decrease by exponentially. Every time a pulse is coming, you have an increase of voltage. Between bursts or between voltage incoming, you have decrease. You have something like this, and when you reach 30, here I don't show when it reaches 30, but every time it reaches 30, it decreases to 0 again. And this is the idea. You can calculate the voltage and also the number of vesicles over time. So given that the number of vesicles is continuous, so they show this pattern that, and given that the maximum is 10, you see here the saturation cannot be greater than 10. And here you see the jumps given the releasing of the vesicles. You can calculate here the variance of the number of, or the voltage over time. Okay, I think that's it, what I wanted to show you guys. So please check the scripts. If you have any particular question, let me know. Thank you so much, guys.